All right, section 11.8, power series. All right, so continuing our discussion of series, a little bit different situation though here. I mean, we're still interested in convergence and divergence of series, so we're going to bring into play some of the things that were learned in the first part of this chapter with different types of series and testing for convergence and divergence. So that's still going to be in play, but we're putting it into a little bit of a different context here, a different situation. Right? So we have the tools to deal with this. So let's broaden the concept. Now, what we call a power series. A power series is a series of the form sum as n goes from 0 to infinity, c sub n times x to the n. Now notice here we're starting with n equals 0. Now, as before, we talked about the indexes on our series. That can be adjusted depending upon the domain of the expression itself. But by default, normally we talked about series being defined for positive values of n, positive integers. Well, for power series, we also include n equals 0. All right, so we've got the sum of n as n goes from 0 to infinity of c sub n x to the n. All right, where these c values are called the coefficients of the series. Those are constants. X is a variable, right, and of course n is our index. So the first term of this series would be c sub 0 times x to the 0. Now remember, anything to the 0 power, any non-zero number raised to the 0 power is 1. So that would give me c sub 0 times 1, or just c sub 0. That's a constant. Plus, we have c sub 1x to the first, plus c sub 2x squared, plus c sub 3x cubed, etc., etc., etc. Right? So the terms of this series, x is a variable, and that's a little bit different than what we've had before, because prior to this, all of our series, once we plugged in the n values, we had constant terms, right? There were no variable terms, so there's a big difference between power series and the series that we've talked about previously. So if we were to fix the value of x, right, then the series would become a series of just a bunch of constants. And then we could test that series for convergence or divergence. Right? So if we fix the value of x, then that brings us right back to where we were before. And we would have a series that we could then, it's a sum of constants. Does the series converge or diverge? What type of series is it? And perform the test, etc., etc. Okay? But that's going to be changing here. So now for a power series, these may converge depending upon the value of x, right? So now if I plug in different values of x, maybe I get a series that converges in some cases and a series that diverges in other cases. So depending upon the value of x that you plug in. So a power series could converge for some values of x, and it could diverge for other values of x. Now again, because of the fact that x is a variable, right, if you look at the sum of our power series, so the sum as n goes from 0 to infinity of c sub n x to the n, it kind of resembles a function, right? Because x is a variable, so I could maybe call this function f of x, whose terms would be the terms of our series, c sub 0 plus c sub 1x plus c sub 2x squared, etc., where we define the domain of that function to be the set of all values of x for which the series converges. All right, so we're tying these two ideas together. So I've got this series, sum as n goes from 0 to infinity of c sub n x to the n. And if I write out the terms of that series, I get c sub 0 plus c sub 1x plus c sub 2x squared, etc., etc., etc. It resembles a function. It is a function of x. And we said depending upon what value of x you plug in, you may get a convergent series or a divergent series. So we're defining the domain of that function to be the values of x that give us a convergent series. Okay. Now note, f does resemble a polynomial function, but there are a couple of differences here. It has an infinite number of terms, so it resembles a polynomial function, but it has an infinite number of terms. And the domain of this function is not necessarily going to be the set of all real numbers. Right, so if I have a polynomial function, right, we have a fixed number of terms. And remember, the domain of polynomial is a set of all real numbers. So those are two differences here. Even though it resembles a polynomial in its makeup, we have an infinite number of terms. It is an infinite series. And how we're defining the domain, the series may converge or diverge. So let's say, suppose in this case that c sub n equals 1. All right, so just to make it a little bit simpler. So our constant, our coefficient of the series for all of our terms is 1. So that would give us 1 times x plus 1 times x squared plus 1 times x cubed, etc., etc. Now the first term is 1 times x to the 0, which again, x to the 0 is 1. So our first term is 1, second term x, third term x squared, etc., etc. So I get 1 plus x squared plus x cubed, and so on and so on and so on. All right, there's at some point our generic x to the n, etc., etc. Now, recognize that as a geometric series. And if you look at the terms of that series, 1x, x squared, x cubed, x to the 4th, etc., how do I get from one term to the next? I'm just multiplying by x. And that's exactly a geometric series, right, where we're multiplying each term by some value to get the next term. Now, what do you know about geometric series? We know that geometric series converge when the absolute value of x is less than 1, right? When r, whatever our constant is that we're multiplying by, is between -1 and 1, or we said the absolute value is less than 1, we have a convergent geometric series. So r in this case is x, because that's what we're multiplying by. So I know then that this series would converge for values of x between -1 and 1, and otherwise it would diverge. So that's just based upon the fact that this series is a geometric series with r equal to x. Now, in the context of the function, since these are the values for which the series converges, then that becomes the domain of our function, f of x, which is defined by that series. Okay? That's the basic idea. That's the idea of how power functions, or how power series work, right? For what values of x does the series converge? And that then becomes the domain of the function that is defined by that power series. So that's the basic gist of it. That's the basic idea. So what's left for us to determine, as usual, is for what values of x does the series converge or diverge. Now, in general, we're going to expand on our previous definition. A series of the form, sum as n goes from 0 to infinity, is c sub n x minus a to the n, which would be c sub 0 plus c sub 1 x minus a to the first plus c sub 2 x minus a squared, etc., etc., is called a power series in x minus a, also called a power series centered at a, also called a power series about a. So you just see different language here. I tend to use the second and third one. I don't typically use the first one. So I'll say a series centered at A, or a power series about A. Okay? But it's a power series of the form, so instead of just x to the n, we have x minus a to the n. Now notice, if n equals 0, the first term would be c sub 0 times x minus a to the 0, right, for n equals 0. And that's just a constant, because x minus a to the 0, remember, now, a little clarification, any non-zero constant raised to the 0 power is 1. So 1 times c sub 0 is c sub 0. So we're taking x minus a to the 0 to have a value of 1, even if x equals a, in this case. Because if x equals a, then x minus a would be 0 as well. And 0 to the 0, that's actually another indeterminate form. And we talked about the indeterminate forms of 0 over 0, infinity over infinity for L'Hopital's rule and all that. 0 to the 0 is another indeterminate form. So that's why you always say a non-zero constant raised to the 0 power has a value of 1. 0 to the 0 is indeterminate. It could be 1, could be something else. For power series, though, we take 0 to the 0 to also have a value of 1. Also, if x equals a, then each term is 0 for all values of n greater than or equal to 1, right? Because if x equals a, then every single term beyond the first term, that would be 0, because x minus a is 0. That would be 0 to the first. And that would be 0 squared and 0 cubed, etc., etc. So every term after the first term would have a value of 0. And so this series then would be c sub 0 plus 0 plus 0 plus 0 plus 0, which would be equal to c sub 0. All right. So this series would converge to c sub 0, right? Because it's c sub 0 plus 0, 0, 0, 0, 0, which would equal c sub 0. And that would be the sum of the series, right? So for the case where x equals a, the series converges, and it converges specifically to whatever that first term is, okay? All right, for example, for what values of x is the series sum as n goes from 0 to infinity of n factorial x to the n convergent? You're going to see a lot of ratio tests with power series in determining convergence or divergence, not exclusively, but you do see a lot of power series, okay? The functions themselves are going to be a little more interesting, right? So that's where ratio test came into play, was when we had factorial, which we have in this case, right? But we said anytime you see combinations of different series or different expressions, ratio test for convergence or divergence. Another reason for the use of the ratio test quite often is, what do we know about ratio tests? Quick review. We take the limit as n approaches infinity of a sub n plus 1 over a sub n, absolute value. We plug all that in, we do a simplification of it, and then once we're done evaluating the limit, ratio test has three different outcomes, right? If the value of the limit was less than 1, we know we had a convergent series. If the value of the limit was greater than 1, we knew we had a divergent series, or if the limit didn't exist. Now, if the limit was equal to 1, remember, though, the series was inconclusive. Right? But what this is going to allow us to do is actually come up with an expression, an inequality, that we can use to determine the values of x for which the series is convergent in the cases where the limit has a value that is less than 1. So ratio test is useful in that sense, right? Because we can actually then set up an inequality that we can use to find the values of x. Because ultimately, again, that's what we're interested in, right? This is a variable series, contains a variable. So it's going to be convergent for some values of x and divergent for other values of x. And that is what is up for us to determine. So we're going to use ratio test. Now again, two different questions here, but they mean the same thing in terms of what we do. Here's our series, sum as n goes from 0 to infinity of n factorial times x to the n. Question, where does that series converge? Or for what values of x does that series converge? Equivalently, the question could be simply find the domain of the f of x, where f of x is defined as that series. So, fat marker, let me bring that down a little bit. Okay? So we're defining f of x, the function f of x, equal to the sum as n goes from 0 to infinity of n factorial x to the n. So find the domain of the function means exactly the same as find the values for x where that series converges, because that's what we define the domain to be. So I'll plug it into the ratio test. Now again, ratio test, limit as n approaches infinity of a sub n plus 1 over a sub n. So n plus 1, a sub n plus 1 would be n plus 1 factorial times x to the n plus 1. A sub n would be n factorial over times x to the n. Now that's in absolute value. Now remember before with absolute value, does a couple things. If we would have any negative terms, like a negative 1 to a power or something like that, then we could apply the absolute value, turn everything positive. I don't have a negative 1 in this case, but I do have an x. Now remember, x is a variable. X could be positive or negative. There's no restrictions on x. That's what we're trying to find, right? We're trying to determine what values of x make this thing convergent, okay? So the absolute value here, I can't just drop them completely. Now I can remove them off of the part of it that contains the n, because the n is going to give us that's always going to give us a positive value. But I do have to keep them around the x. Now also reminder, we talked about n plus 1 factorial before. We said n plus 1 factorial is equal to n plus 1 times n factorial. You also have the fact that 0 factorial is equal to 1. You can plug that into the calculator if you want to check that, but by definition, yeah, even though remember factorial is defined to be what 1 times 2 times 3 times 4 times 5, etc., 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 0 factorial is also defined to have a value of 1 as well. Go figure. So that gives me the limit as n approaches infinity, and again, all I did was, the typical simplification we did with these terms. So the n plus 1 factorial becomes n plus 1 times n factorial. X to the n plus 1 becomes x to the n times x. And so that allows us to do some simplification, right? We can divide out the x to the n, we can divide out the n factorial, and that leaves us with this limit as n approaches infinity of n plus 1 times x. Now again, I'm keeping the absolute value because of the x. Now one of our basic properties of absolute value, so maybe again a quick review. The absolute value of a product is equivalent to the product of their absolute values. So in other words, the absolute value of n plus 1 times x, I'll go ahead and include my limit statement here, can be written as the absolute value of n plus 1 times the absolute value of x. All right, so the absolute value of a product is equal to the product of the absolute values. Now, n plus 1 we know is always going to be positive. All right, because as n goes from, originally our series was what, sum as n goes from 0 to infinity. So even for n equals 0, the first term there would be 1. So n plus 1 is always positive, so I can drop that absolute value, but I have to keep the absolute value around the x. And that's the important thing to remember with these guys, because x is a variable. It could be positive or negative. I have to keep the absolute value on that. So that gives me the limit as n approaches infinity of n plus 1 times the absolute value of x. Now, n plus 1 as n approaches infinity, that's going to go to infinity, right? So I've got infinity times absolute value of x, whatever x is irrelevant. If n approaches infinity, this entire expression approaches infinity. Okay. Now, this is the result of your ratio test. So that tells you that that series is divergent. Now, it's divergent for all values of x except necessarily 0. That's going to go back up here. Now, why did I leave 0 out up here? Because of this. So here is our limit as n approaches infinity of a sub n plus 1 over a sub n. Well, if x equals 0, that's undefined. All right, so I can't evaluate that limit for x equals 0. So you have to be on the watch for things like that as well. I mean, we still have basic algebra in play. So that when I evaluate this limit, and I apply a ratio test and so forth, and we simplify, we get a limit equal to infinity. So that tells us that this series would be divergent for all values of x that are not equal to 0. Well, what happens at x equals 0? So I'm going to have to test that separately. Right? So it may be that I am not able to test every single value using the same test. And that's going to be typical. I mean, what's going to happen, maybe I can use ratio test to test the majority of values, but I may end up with a few values that I'm going to have to test individually. And that's the case here. So what happens for x equals 0? Well, for x equals 0, we go back to the original series and plug it in. So that gives me the sum as n goes from 0 to infinity, n factorial 0 to the n, right? All I did was plug in 0 in place of x. But we defined 0 to the 0 for n equals 0. We said 0 to the 0 would have a value of 1. And we also defined 0 factorial as having a value of 1. So for n equals 0, I've got 0 factorial times 0 to the 0. But both of those, by definition, we said have a value of 1. Now, for n equals 1, 2, 3, etc., I've got 0 to the first, 0 squared, 0 cubed, 0 to the fourth, etc., right there. So all of those terms would be 0. Times n factorial would give me 0. So the first term, when n equals 0, is 0, is 1. And every successive term would be 0. And so our series would be equal to 1 plus 0 plus 0 plus 0, et cetera, et cetera, et cetera, which is convergent, right? It converges to 1. The sum is 1 there. So that tells us then that this series is convergent for x equals 0, and it's divergent for all other values of x. So the series only converges for x equals 0. And therefore, the domain of our function f of x, which was defined by that series, is 0, because that is the only value for which that series converges. For what values of x does the series sum as n goes from 1 to infinity of x minus 3 to the n over n converge? Notice here we're starting at n equals 1, and that's simply because of domain issues, because if n was 0, the first term would be undefined, right? So as we said before with this, typically with power series, we would like to start at 0, but we can adjust that depending upon the domain of our series. Same thing we said before with series in general. We typically start at n equals 1, but sometimes we had to adjust that because of the domain. So nothing major there. All right, so here's our series. We're testing for convergence or divergence of that power series. And also alternatively, we could say find the domain of the function f of x defined by that power series. So again, I'm going to use our ratio test. Right? So we got the limit as n approaches infinity. I've got n minus 3 to the n plus 1 over n plus 1 over a sub n, which is x minus 3 to the n over n. Okay. So then we'll take our limit as n approaches infinity. I'm just multiplying by the reciprocal, as we typically do. Now again, this is just right back to using ratio test as before, right? So nothing changes in terms of ratio test. We just have to keep track of that x. That's the only difference. So there's a sub n plus 1 divided by a sub n, or a sub n plus 1 times the reciprocal. Now again, I can rewrite x minus 3 to the n plus 1 as x minus 3 to the n times x minus 3. I can write, that's fine. So when I get to this point, and I've got the n over n plus 1 times x minus 3 to the n plus 1 over x minus 3 to the n, I can divide out the x minus 3 to the n, leaves me with x minus 3. Now again, the absolute value is still there around the part containing the x. And I've got the limit as n approaches infinity of n over n plus 1 times the absolute value of x minus 3. Now, a difference in, again, properties of absolute value. We said the absolute value of a product is equal to the product of the absolute value. So if I had the absolute value of 3 times x, then that would be equivalent to the absolute value of 3 times the absolute value of x. That's not true for sums and differences, though. In other words, the absolute value of x minus 3 is not equivalent to the absolute value of x minus the absolute value of 3. Okay? So I can't rewrite this. I'm leaving it as absolute value of x minus 3 times n over n plus 1. Now, the n over n plus 1 part, as n approaches infinity, we've done enough of those. When you could divide everything by n, you get 1 over 1 plus 1 over n. Well, the limit as n approaches infinity, that is 1 times the absolute value of x minus 3. So that gives us x minus 3 as the value of this limit as n approaches infinity. Now, here's where we bring in, like we said, what we know about ratio test. Ratio test says that if the limit is less than 1, we have convergence. If it's greater than 1 or does not exist, we have divergence. If it equals 1, it's inconclusive. All right, so we know that this would be convergent then. We would have absolute convergence, technically, when the absolute value of x minus 3 is less than 1. All right, so that's the one that we're interested in. So then we said also, again, it's divergent if it's greater than 1. So set up our inequality. X minus 3 absolute value is less than 1. which means x minus 3 would fall between negative 1 and 1, and we solve that inequality and we get x between 2 and 4, right? Just adding 3. So those give us the values of x for which this series is convergent. We know it's convergent between 2 and 4. That would also mean that for x values less than 2, for x values greater than 2, if I go outside of that interval, we would have divergence, right? But again, all I care about is where is it convergent. Now, you also have to check your endpoints here, right? Because we know it's convergent where the absolute value of x minus 3 is less than 1. What if the absolute value of x minus 3 equals 1? Right? Remember, ratio test said it's inconclusive. So we're going to have to check each of the endpoints. This is the part not to forget, and I see a mistake with this all the time. Even if we get comfortable with the idea of, okay, I'm using ratio test, and where's that thing less than 1, don't forget you also still have to check the endpoints, because where x minus 3 equals 1, this test is inconclusive. So check your endpoints where x equals 2 and where x equals 4. Those were the endpoints of our interval. So when x equals 2, I've got the sum as n goes from 1 to infinity of 2 minus 3 to the n over n. Remember, our series was x minus 3 to the n over n. So I'm just plugging in 2 in place of x. I've got 2 minus 3 over n. That'll give us negative 1 to the n over n. And here's where you bring in your other tests. And that's an ideal test for alternating series tests. Right? Absolute value of negative 1 to the n over n is 1 over n. Limit as that approaches 0, as n approaches infinity, is 0. And those would be decreasing terms. But that goes back to your understanding of alternating series tests. That's nothing new. So I could show that this converges by alternating series tests. And then I plug in x equals 4. That's the other endpoint of our interval. And for x equals 4, I then get the sum as n goes from 1 to infinity of 4 minus 3 to the n over n, which is the sum as n goes from 1 to infinity of 1 over n. Now that's our divergent harmonic series, right? So again, everything, you're going to have to rely upon what you know from previous tests for convergence of series. So therefore, I could say that this series converges for all values of x between 2 and 4, and it converges also for x equals 2. So the domain of the function defined by that series would be the interval from 2 to 4, including 2, but not including 4, because that's where the series is convergent. That's the idea. That's a typical power series type question. Now, another use for power series, and this we're going to talk a little bit more about in the next section. Power series allow us to represent many important functions in math, in physics, and so forth. All right, so functions that cannot otherwise be represented, such as what is called the Bessel function. Right? If you delve into physics, any kind of upper level physics, you'll probably run into this Bessel function. Bessel function, this one's called the Bessel function of order 0. It is the sum of a power series. Notation, j sub 0 of x, j obviously for Bessel, is equal to the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n over 2 to the 2n times n factorial squared. That's a pretty function. Question, find the domain of that function. All right, so again, that means the same as find the values for x for which that series converges. Now again, the Bessel function I'm not particularly interested in specifically here. It's just an example of a function that's used in physics that is actually the sum of a power series. So plugging it into our ratio test, limit as n approaches infinity of a sub n plus 1 over a sub n. Right, or in this case, I went ahead and wrote out the a sub n plus 1 times the reciprocal of a sub n to get to this part. And then again, the usual simplification with all of this stuff. Now, I've got -1 to the n plus 1, x to the 2 times n plus 1. So that's x to the 2n plus 2. I've got that 2 raised to the 2 times n plus 1. So I went and wrote that as 2 to the 2n plus 2. We've got, and then the other terms, I went and brought over the 2 to the 2n. We've got the n factorial squared. We've got the n plus 1 factorial, or n plus 1 squared, rather. N factorial squared times x to the 2n. Okay, I have everybody accounted for over there. Now, yeah, so I guess this n plus 1 factorial squared, that's this guy. Because remember, n plus 1 factorial means n plus 1 times n factorial. And we had that in the earlier one. And then I applied the power rule, the rule of exponents, right? So a product to a power, I get n plus 1 squared times n factorial squared. So that allows us to divide out the n factorial squared. That's gone. I can divide out the 2 to the 2n, which would leave me with 2 squared. Let me maybe write this out, because I don't... Again, I'm going to leave off the limit just so I have room over here to write this. Because I think maybe if I write this in more detail as far as how did I get from this to what's below it. So x to the 2n plus 2 is x to the 2n times x squared. And then we've got the 2 to the 2n. And we've got the n factorial squared. In the denominator, I've got 2 raised to the 2n plus 2. So that is, again, 2 to the 2n times 2 squared, right? So remember, we've done that before with things like 2 to the n plus 1 would be 2 to the n times 2. And the same thing here. And then we've got the n plus 1 squared and the n factorial squared, which I explained where that came from. All right, so just a little clarity on that. I think I skipped a step in writing all that out in detail. All right, so now we're able to divide out the x to the 2n, right? So I left that off. So that's gone. Our 2 to the 2n, that's gone. The n factorial squared, that's gone. So we're left with x squared over 2 squared n plus 1 squared. Now also notice I've dropped the absolute value. Now even though there's still an x in there, right, the absolute value takes care of the -1, right, so I don't need that anymore. But then also I'm able to drop the absolute value here because notice the x is being squared. Whether it's x to the 2n plus 2 or x to the 2n or what have you, that's x raised to an even power, which is always positive. Right? So you can again make use of observations like that to say, well, hey, since x there is raised to an even power, I know it's always a positive value. I don't need the absolute value anymore. So that just simplifies it a little bit. So that gives us the limit as n approaches infinity of x squared over 2 squared times n plus 1 squared. That gets us down here. Now, as n approaches infinity, that's going to go to 0, right? Because the only n I have in this thing is here. So as n approaches infinity, that's going to go to 0. I don't care what the value of x is. That's not going to change a thing. So this is equal to 0 for all values of x. And then because this is the result of a ratio test, it's the value of the limit. Don't forget what your objective is here. That is the value of the limit. Ratio test says compare it to 1. And if that's less than 1, you have convergence. In this case, it's convergence for all x. Because regardless of the value of x, that's always going to approach 0. So therefore, this series converges for all values of x. And we would say then that the domain of that Bessel function order 0 is a set of all real numbers. And I just threw in the Bessel function order 1 just to show you the difference, so all you're doing is increasing the, the exponent by 1. Right? Not important for our purposes, but just to throw that in there. All right, so here's the big takeaway from all of this. So there's a couple of examples, and we're going to do some more. We've got a theorem that tells us that for any given power series of this form, sum as n goes from 0 to infinity of c sub n times x minus a to the n. There are only 3 possibilities in terms of convergence. Either the series converges only when x equals a, so it only converges for a single value, or the series converges for all x, like the one that we just found, right? Converge for all real numbers. Remember, we had that one earlier that converged only when x equals 0, so that would be the case in number 1. Or there is some positive number r such that our series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. That was from our power series. Remember, r would be 1 because that's what we compared it to. All right, the one we had earlier where the absolute value of x minus 3 was less than 1 because we were using ratio test. That would be our r value. And then we find the interval over which our series converges. Right? So there's only 3 possibilities. Either your series converges at a single value for f(x), it converges for all values of x, right, for the entire set of real numbers, or it converges on some interval, which we could define or determine based on this r value. Now, this r value is called the radius of convergence of your series. All right? And in our first case, r would be 0 because, again, you're only converging for a single value. And so we say that r in that case equals 0. In case number 2, where we're converging for all values of x, r is infinity. Now we're converging for all values of x from negative to positive infinity. R is infinity. The radius of convergence probably makes more sense in case 3, where we're converging on an interval. In that case, of the one that we looked at, where the absolute value of x minus a was less than 1, I'm converging for all values within a distance of 1 unit, right, of our a value, which was 3 in that case. And then remember, we converged on the interval from 2 to 4. So r was 1 unit on either side of 3. That probably makes a little bit more sense. But notice also I have for case 1, all right, our interval of convergence, since we're only converging for a single value, whatever the a value is, a then is our interval of convergence. It's a single value, right? But it's the interval of convergence. And then, like we said in the second case, where r is infinity, where we're converging over the entire set of real numbers, then that's our interval of convergence. And again, that I think makes sense. Now, to determine that interval of convergence in case 3 especially, that's where we took our absolute value of x minus a less than r, once we determine what r is, to find the actual interval of convergence. And then, like we said, we could have convergence at the endpoints or not. Right? So not only do you have to determine the interval of convergence, but you may also have to check the endpoints. Now, we had a couple of cases that had intervals of convergence. I'll summarize those on the next page, but remember the first one that we did was a geometric series, converged for x between -1 and 1. We didn't have to check the endpoints on that case because, like we said, it was a geometric series. And we've already established that geometric series are convergent for r values between -1 and 1. Or in that case, it was x between -1 and 1. So our radius of convergence would still be 1, right? It's within a distance of 1 unit. But you may have to check the endpoint, as we did if we're using ratio test. All right. So where is the absolute value equal to 1? We do have to check those individually. So like I said, this is the summary for the ones that we've done up to this point. In that first example that we did, we had the geometric series. The sum as n goes from 0 to infinity of x to the n. And we showed that that series converged to values of x between -1 and 1, r equals 1. Notice in this case our c value, because remember we're talking about something of the form c sub n times x minus a to the n. Notice a is 0 in that case, because it's just x to the n. So x minus a is 0. And so we're within a distance of 1 unit of 0 of the a value. And that's why the terminology we use, we said it's a series centered at a or a series about a. Okay. And so that comes into play when we talk about this radius and interval of convergence. The second one we did was a n factorial x to the n, right? And we found that it was convergent only for x equals 0, right? That was the only value for which it was convergent. So that's why we said since there's only a single value for convergence, then the radius of convergence would be 0. Right? There's only one value that we have convergence for. Number 3, that was when we applied the ratio test, x minus root of the n over n, and we found that it was convergent over the interval from 2 to 4. But initially, we ended up with the absolute value of x minus 3 less than 1, right? So there was our x minus a less than 1. A is 3. Radius of convergence would be 1. That's what we're comparing it to. And we ended up with the interval from 2 to 4, which notice is in a distance of 1 unit on either side of 3. Now that one was the case where we had to check the endpoints because that was the result of a ratio test. And we had to plug in 2 and 4 to check the specific series. And the last one was that Bessel function, where we found the function, the series was convergent over the entire set of real numbers. So that would be our interval of convergence, and our radius of convergence would be infinite. So infinity. All right, so with all that, let's do one more. We'll find the values for which the series converges. We're also interested, I'll ask you this time, for the radius and interval of convergence. Right, so a good test question, obviously, not just finding the domain of the function, find where the series converges, or find the radius of convergence, interval of convergence. It's all the same process. It's just a matter of answering the question. So here I've got the sum as n goes from 0 to infinity of -3 to the n times x to the n over the square root of n plus 1. So again, I'm using ratio test here for 2 reasons. First of all, it's a lot of different parts to that series. Secondly, ratio test allows us to make that comparison to 1, which helps us set up that radius and interval of convergence when you can use it. Now, like I said, it's not exclusive, but it is very often the test that we use. So we'll take our limit as n approaches infinity of a sub n plus 1 over a sub n, or in this case, times again the reciprocal. So a sub n plus 1 is -3 to the n plus 1 times x to the n plus 1 over the square root of n plus 1, which gives us the n plus 2. Divided by a sub n, or times its reciprocal, which would be the square root of n plus 1 over -3 to the n times x to the n. Now, going through our typical simplification, we've done enough of these now. We should kind of see how these are working. I've got a -3 to the n plus 1, and I've got a -3 to the n. I can divide out the -3 to the n, leaves me with -3 to the first. There. We've got an x to the n plus 1 over x to the n. We can divide out the x to the n, which leaves us with x. And then I went ahead and combined the square roots into a single fraction. I've got square root of n plus 1 over square root of n plus 2. So I just went ahead and put those together. Now again, I need to keep the absolute value here because of the x, but because of the x only. So there's a product. There's an absolute value of -3 times x times the square root of n plus 1 over the square root of n plus 2. That's a product, so I can take the product of absolute values. The absolute value of negative 3 is 3. The absolute value of x, that's where I have to keep the absolute value because we don't know what x is. It could be anything. And then the square root of n plus 1 over n plus 2, I don't need absolute value on that for two reasons. First of all, the radicand there is positive, n plus 1 over n plus 2 for all values of n. Secondly, it's a square root, which is a positive value always, or at least over its domain. All right. And we're not dealing with imaginary numbers here. We're dealing strictly with positive numbers. We're not interested in finding values of convergence that are non-real numbers. So don't even think we're going to go there. But I do need to keep the absolute value about the x because, again, x is variable. Now, the limit as n approaches infinity, the square root part, we can evaluate as we always have. I can divide everything by n. So I got 1 plus 1 over n, 1 plus 2 over n. So as n goes to infinity, that's going to approach 1. And that leaves us with 3 times the absolute value of x. As n approaches infinity. Now again, this is the result of the ratio test, right? So the ratio test says we have convergence if the limit is less than 1. Now in terms of interval and radius of convergence, notice I first solve for the absolute value. So 3 times the absolute value of x is less than 1, which means the absolute value of x is less than 1/3. There's your r value. Right? Remember, the r value comes from the absolute value of x minus a being less than some constant. Now, a in this case, again, would be 0, x minus a. But our absolute value has to be less than 1/3. That's our radius of convergence. So therefore, we know that this series would be convergent if x is between negative 1/3 and 1/3. That's our radius of convergence. Now, because again it's ratio test, I do have to check the endpoints, because where it's equal to 1 would be at negative 1/3 and positive 1/3. That's inconclusive, so I've got to check each individually. So for x equals negative 1/3, if I plug that into my original series, I've got negative 3 to the n times negative 1/3 to the n. Remember, it was negative 3 to the n times x to the n over the square root of n plus 1. So I'm plugging in negative 1/3 in place of x. I've got negative 3 to the n times negative 1/3 to the n over the square root of n plus 1. Now, negative 3 times negative 1/3 is 1. All right, so that would just be 1 to the n over the square root of n plus 1, or 1 over square root of n plus 1, or 1 over n plus 1 to the 1/2. Recognize that is a p-series. All right, n to the 1/2, n plus 1 to the 1/2. There's no difference there. But it's a p-series with p equal to 1/2, which we know to be divergent. All right, because remember, your p-series diverges for p-values less than 1, less than or equal to 1, excuse me, and converges for p-values greater than 1. So that is a divergent p-series. We then check x equals 1/3, our second endpoint. And for x equals 1/3, I've got negative 1 to the n instead of positive 1 to the n. I guess maybe I should write that out. Let's see. Let me put it down here. So I've got that sum as n goes from 0 to infinity of negative 3 to the n times now positive 1/3 to the n over that square root of n plus 1. All right. Now, so just as before, when we multiplied by negative 1/3, we got positive 1 to the n. Here it's negative 3 times 1/3, so that's where I'm getting 1 to the n, which is just 1. And let's see where we're at. Yep, that's this guy. All right, so for x equals 1/3, so it'd be negative 3 times positive 1/3 gives us negative 1 to the n. Now that one I'm going to have to use alternating series test for. Right, we already know that 1 over positive 1 over square root of n plus 1 is a divergent p series. Negative 1 to the n over the square root of n plus 1 requires alternating series test because of that negative 1. So the absolute value of that would be 1 over square root of n plus 1. Remember, alternating series test, you're checking two things. First, are those decreasing? And yes, as you increase n, 1 over the square root of n plus 1 decreases. Secondly, the limit has to approach 0. The limit as it approaches infinity of 1 over the square root of n plus 1. That is 0. It meets the two criteria for convergence by the alternating series test. And so our interval of convergence was negative 1/3 to 1/3. Right? That was our absolute value of x was less than 1/3. So negative 1/3 to 1/3. And then we checked each of the endpoints and we showed that it was convergent if x is positive 1/3 and divergent if x is negative 1/3. So that would be our interval of convergence. Right? And that would also be the domain of the function defined by that series. So if we called that f of x and said find the domain of that series, the domain of that series would be negative 1/3 to 1/3, excluding negative 1/3 and including 1/3. Okay? There's your power series.